Welcome to the Insightful Professor. With this video, we begin a new series on topics in cybersecurity. Our focus is going to be on data security. So what do we wish to accomplish with this video series? Well, we want to provide an understanding of why computer systems are sometimes insecure and how we might be able to make them better. To achieve this understanding, it's necessary to recognize what might go wrong, what kind of attacks we might be subjected to. So in this series, we will address computer security in general, but our emphasis will be placed on the protection of data. When appropriate, we will be using Oracle database as a tool or as an environment to demonstrate aspects of computer security and the protection of data. Let's begin with an overview of computer security. Computer security deals with computer-related assets that are subject to a variety of threats and for which various measures are taken to protect those assets. What do we really mean by computer security? To answer this question, we consider three fundamental points. What computer-related assets do we need to protect? How are these assets threatened? What can we do to counter these threats? Security in general is about achieving some goal when there is an adversary present. This adversary wants to make sure you are unable to use the system to accomplish tasks such as accessing data, to answer questions, or maintaining data that you have in your possession. Think about the types of data you have entrusted to electronic systems and how you interact with these systems. We have social media, personal information about us, email, correspondence with others, banking systems, financial data like savings or checking accounts and credit cards, e-commerce, online purchases. This short list identifies only a few electronic systems with which we might interact. Our goal is to achieve a secure system. A secure system is one that allows us to do something regardless of the goals of the adversary. A secure system is a system that can continue to operate despite attempts by this adversary to thwart our activity or use of the system. So what is necessary to achieve a system with security? So we consider this from three components or capabilities. First, a security policy. This is a statement about capabilities of the system, what it can do. A security policy defines a goal you wish to achieve. It will address things like confidentiality of data, the integrity of data, the availability of the system itself. Second is a threat model. This would be a set of assumptions about the adversary, what the adversary might attempt to do. The threat model could be non-trivial, which means we need to consider what the adversary can do, and this involves identifying vulnerabilities of the system. This also means that we have to accurately and completely respect the capabilities of the adversary. So our threat model must reflect all of the potential capabilities. Thus, provided the threat model is correct, the final component is the mechanism. This might take the form of software or hardware to ensure that the policy is achieved as long as the adversary follows the threat model. This may seem rather simple and easy to achieve. However, there are significant challenges that add to the difficulty of achieving security as we've outlined it here. We must ensure that the security policy is followed regardless of the capabilities of the adversary. We note also that the system simply enforces the policy. It does not dictate the policy. The policy is dictated by the organization or individual who wishes to employ security. So to achieve our goal under a set of assumptions, some mechanism is required that's going to try to make sure our policy is followed, provided the adversary follows the threat model. The result is, if our threat model is correct, and if the mechanism does not fail, we will satisfy our policy. FIPS are standards and guidelines for federal computer systems that are developed by the National Institute of Standards and Technology, NIST, in accordance with the Federal Information Security Management Act. These standards and guidelines are developed when there are no acceptable industry standards or solutions for a particular government requirement. Although FIPS are developed for use by the federal government, many in the private sector voluntarily use these standards. The NIST standard FIPS 199, the Standards for Security Categorization of Federal Information and Information Systems, lists confidentiality, integrity, and availability as the three security objectives for information and information systems. Confidentiality refers to preserving authorized restrictions on information access and disclosure. This includes protecting personal privacy. Integrity guards against improper information modification or destruction. And availability ensures timely and reliable access to and use of information. These three concepts embody the fundamental security objectives for data and for information and computing systems. They form what is often referred to as the CIA triad. So according to FIPS 199, a loss of confidentiality is the unauthorized disclosure of information. A loss of integrity is the unauthorized modification or destruction of information, and a loss of availability is the disruption of access to or use of information or an information system. NIST offers many publications that may be useful to anyone interested in understanding cybersecurity and establishing a security policy. We will refer to several NIST publications throughout our discussion of data security. You can access these documents through the NIST website. This slide shows how to initiate a document search for the NIST standard FIPS 199 we referred to on our previous slide. After entering the URL as shown here, we choose the advanced search option, enter NIST Pub Series, and we're putting FIPS in there. Select the report number, and we've provided 199. Click the search button, and you should find the document. And you should be able to access and download that for viewing. While confidentiality, integrity, and availability constitute the fundamental security objects, we wish to present a more complete picture of security requirements. Authenticity means verifying users are who they claim to be, and that each input arriving at the system came from a trusted source. We examine authenticity from the perspective of users connecting to a system. With respect to accountability, we'll discuss audit data collected by systems. Because truly secure systems are not yet an achievable goal, we must be able to trace a security breach to a responsible party. Systems must keep records of their activities to permit later forensic analysis to trace security breaches or to aid in transaction disputes. At the start of this video, we noted that our goal is to provide the viewer with an understanding of why computer systems sometimes are insecure and how they might be made better. Furthermore, we indicated that to achieve this understanding, it's necessary to recognize what might go wrong. We noted that building a system with security required considering three components: a security policy, a threat model, and a mechanism. As we now consider what might go wrong, we'll examine each one of these components to see where potential vulnerabilities or problems might exist. We first consider problems that might occur with a security policy. As an example, we'll start with Sarah Palin's email account. Sarah Palin was a United States vice presidential candidate in 2008. On September 16, 2008, her Yahoo personal email account was subjected to unauthorized access. Information about this event can be found at the URL we've listed here. Here's where the problem begins. Yahoo email accounts have a username, a password, and also security questions. A user can log in by supplying their username and password. If a user forgets their password, they can reset the password by answering security questions. In the event we're referring to here, the hacker had obtained access to Palin's account by looking up biographical details such as her high school and birth date and using Yahoo's account recovery for forgotten passwords. The hacker then posted several pages of Palin's email. The problem is that sometimes security questions can be easier to guess than a password. Things such as an individual's high school and birth date, especially when it's a prominent individual, such as a vice presidential candidate, might be easy to obtain. So the security policy that we encountered here was a user can log in with either a password or by answering security questions. In another event, Matt Honan, who is a writer for Wired, had a problem that occurred in 2012. A series of events occurred in which he stated this destroyed his digital life. The problem that occurred here resulted from multiple services or systems. Each by themselves seemed to have a reasonable policy. However, the policy of one system was adversely affected by that of another system. The problems that Matt Honan experienced consisted of his Google account being taken over. A Twitter account was compromised and used to broadcast messages. An Apple ID account was broken into, and data there was erased from his iPhone, his iPad, and his MacBook. How did all of this happen? Consider what happens when you lose your password to your email account for some service. You might have another email account through which you could receive your lost password. This was kind of the basis for this particular attack. To find out details about this, and it's a very interesting story to read about, visit the URL we've listed here. What we wanted to do in these two slides was not go into exhaustive detail about the actual events, but show you that security policies if not defined precisely, if not considering what the threats are, what the capabilities of the adversary might be, these can introduce vulnerabilities to the security of your data. Let's take a look at possible problems with the threat model. A big issue in practice turns out to be human factors. Often we make assumptions about what people will do in a system, and these are assumptions. We assume they'll pick a good, strong password. We also assume that they will not click on random websites obtained through email and supply their password there. However, in practice, these are not good assumptions. People often pick bad passwords. They pick weak passwords. People will click on random links. People will enter their password on sites that are actually not the right site. They don't always pay attention. Sometimes it's very obvious if they look carefully, but many times it's not so obvious that they've entered an incorrect site. So a threat model that makes assumptions about what humans will do will inevitably result in something going wrong. Also consider that the threat model is not necessarily a one-time event, but it has to be reevaluated. Sometimes threat models will change over time. So an assumption made at the time a system is developed and deployed might be reasonable. However, as time moves forward, the assumption could become invalid. Consider the size of an encryption key. At one time, a 56-bit encryption key, a 56-digit binary number, was deemed unbreakable. Hence, it provided good security. But with the increasing speed of computers, a 56-bit key became breakable in a very short period. So a policy based on an assumption, such as a 56-bit encryption key being unbreakable, should be reevaluated over time. And finally, there can be problems with the mechanism that is used to enforce the policy against the perceived threats. People often pick weak passwords. The password can be guessed with a few attempts. Most services have a rate limit in terms of the login attempts. This would be the number of times a username and password are supplied as invalid. Typically, what will happen is the account becomes locked or some other action is taken, which effectively will deter the guessing of passwords. A situation where this arose occurred with Apple iCloud and the password guessing rates. There was an application called Find My iPhone. This particular application forgot or neglected to implement login rate limiting. If you'd like to read more about this, I've provided a URL here. But in general, the problem we've described here is a result of a situation where a secure system should limit the attempted number of logins and then freeze the account for some period of time. Apple's iCloud service had many different APIs or programming interfaces. iCloud could be used for file storage, photo sharing, and other interfaces. These interfaces want to make sure that you are the right user. You are authenticated correctly. What was discovered here was that the Apple iCloud service did not enforce the same sort of mechanism at all interfaces. The Find My iPhone was an interface where they neglected to support the policy. So this is sort of an example of you've got the right policy. Only the user and the right password would get you access to the files. You even got the threat model correct. The adversary might be able to guess the password. So we need to limit the number of guess attempts. What happened was perhaps an oversight. The developer forgot to enforce this policy and mechanism at some interface, the Find My iPhone interface. Dorothy Denning, in her book, Cryptography and Data Security, provides this definition of data security. Data security is the science and study of methods of protecting data in computer and communication systems from unauthorized disclosure and modification. From Denning's definition of data security, we see that data might reside within a computer, but it might also be transmitted to another computer. Now, data security involves legal, social, and ethical issues. For example, does the person making the request have a legal right to the requested information? Some information may be deemed to be private and cannot be accessed legally by unauthorized organizations or persons. There's also a concern for the protection from inference. Does information available to a user allow that user to derive other information to which the user might not have direct access? Let's consider how data might be transmitted between computers on a network. The diagram shown here presents a simple two-tier client-server architecture. In practice, this architecture is often extended to more than two tiers, but this basic diagram will suffice for our purposes. The architecture consists of two components or processes. The client, which runs the application that interacts with a user and requests services of the server. This could be something like a web browser. The server runs the software that provides services for a user. This could be a social media service, an email server, a banking system, or some other service. The client could be almost anything today: a PC, workstation, laptop, a mobile device like a smartphone, or even a home appliance. Perhaps you've heard the term Internet of Things. We'll discuss that topic in a little bit more detail in a later video. In the middle of the diagram connecting the client and the server, we present the network. The network could be local to a business or organization, or it could be the internet. When the client sends a message, it will be placed in a packet and shipped across the network. Within the network, this packet may pass through several intermediary devices before it ultimately arrives at the destination server. Let's consider some general security issues that pertain to the protection of data. Data security addresses many issues. These include physical control, such as limiting access to computer facilities. Then there are policy questions. How is it decided who should be allowed to access what? For example, credit ratings and personal medical records. Does the organization identify multiple security levels and categorize data and users based on these classifications? For example, in government and military installations, we often see classifications such as top secret, secret, confidential. The security policy of the organization with respect to permitting access to various classifications of data must be enforced. There are also operational problems. How are passwords kept secret? How often are passwords changed? Does multi-factor authentication apply? For operating system support, we consider such things as, does the underlying operating system erase the contents of main memory and disk files when finished with them? I remember in my own personal employment working with IBM mainframe software. IBM supported an access method called VSAM, Virtual Storage Access Method. This was back in the 1980s. They had the ability to specify when a file was deleted, would the disk space occupied by that file be overwritten with binary zeros? Simply deleting a file removes it from a directory, but does not necessarily alter the physical storage that was occupied by the data. So this mechanism, this concept of overwriting the storage area, I remember this back in the 1980s when I worked on the mainframes. And that was well before we had concerns to the extent that we have today with data security. Achieving the protection of data in computer and communication systems from unauthorized disclosure and modification means the information content entrusted to the database is protected in some way. But how is it protected? Data security can be thought of it as encompassing 4 kinds of control: access controls, information flow controls, inference controls, and finally, cryptographic or encryption controls. Security threats might be considered non-fraudulent or accidental, or fraudulent, intentional. Non-fraudulent threats are casual accidents independent of a determined will to cause damage. These can consist of such things as natural or accidental disasters, errors or bugs in hardware or software, human errors. Fraudulent or intentional threats denote an explicit and determined will to cause damage. These threats could result from 2 user classes: authorized users who abuse their privileges and authority, effectively insiders, and hostile agents, improper users, typically outsiders, but could also consist of insiders. The nature of the threats and the incidents for hostile agents include acts of vandalism, improper reading or writing of data, legal tasks or legal use of applications that mask the real fraudulent purpose, and also malicious software in the form of viruses, Trojan horses, and trapdoors. Flow controls serve to regulate the distribution or the flow of information among accessible objects. A flow between some object that we might refer to as X and some other object that we might refer to as Y occurs when a statement reads values from X and writes values into Y. X and Y, in this case, could very well be different files. I read a value, a record, some data from file X and deposit it or write it into file Y. What's the significance of doing this? It doesn't seem that harmful. Well, suppose some users, and only some users, can access X, but other users, the majority of users, could access Y. I'm actually transferring data from a more secure or more private container to a more public container. Flow controls check that information contained in some objects does not flow explicitly or implicitly into these less protected objects, these more public objects. If not controlled, this flow of information could lead to a violation of secrecy or confidentiality. Inference controls aim at protecting data for indirect detection. Inference occurs when a set of data items read by a user can be used to obtain another set of data items. Here we're referring to these as X and Y, and we're saying that Y is effectively derived from X. The main inference channels in a system include indirect access, which occurs when an unauthorized user succeeds in determining the set of data for which he or she is not authorized through some type of a query on a set of data that is visible to this user. Another example could be the insertion of a record having the same key of an already existing record that is not visible to the user making the insertion. Upon system denial, the user now infers the existence of a record that he cannot access. Correlated data. Visible X data are semantically connected to invisible Y data. That means information about Y can be obtained by reading X. And finally, missing data. An example is answering a query by displaying, together with authorized information, null values, which mask the sensitive, inaccessible information. These null values make it possible to infer the existence of the masked item value, sometimes the value itself, or at least decrease the uncertainty about it. Access controls are responsible for ensuring that all direct accesses to objects occur exclusively according to the modes and rules fixed by the protection policies. Access control includes subjects who access objects through operations. Subjects could be users or processes running within the system. Objects would consist of data or perhaps programs. And operations might include such things as read, write, and execute. Functionally, an access control system consists of two components: a set of access policies and rules, information stored in the system, stating the access modes to be followed by subjects upon access to objects, and a set of control procedures or security mechanisms that check the queries or access requests against the stated rules, kind of a query validation process. Queries may be allowed, denied, or modified, filtering out unauthorized data. Now, while the security controls can enhance the protection of data, we want to emphasize that security controls come at some cost. They entail additional execution time on the system. So it's important to minimize this time to avoid a negative effect on system performance. When we talk about things like encryption, this refers to the process of transforming information into kind of a disguised or unreadable format. So encryption is the process of transforming information using some algorithm to make it unreadable to anyone except those individuals that possess that special knowledge in the form of a key that controls the execution of the algorithm. But the point that we're talking about with encryption and system resource is an encryption is basically a process. So the process of encrypting is going to consume some system resources. Once we have the data in this encrypted format, we need to decrypt it to restore it to a readable, meaningful format. This also entails some process that runs within a system. So even with knowledge of the encryption key, the processes of encryption and decryption require processing or execution time. Encryption is very useful, and we'll discuss this in some detail. This can be applied to data at rest, data stored on, say, some secondary storage device, but it also can be used to protect data in transit, data being sent across the network. Previously, we referred to putting the data within a packet, and the packet gets shipped across the network. We could encrypt the content of that packet. From a standpoint of acceptability of security controls, in particular encryption, this additional overhead contributes often to folks rejecting security controls because it adds too much overhead to the system. From a security perspective, given a complex algorithm and key, encrypted data are protected against unauthorized use. This is because without knowledge of the encryption key, the amount of time required to make the information understandable is prohibitive. Note that security is not an absolute. We often use the terms strong and weak to refer to the difficulty faced by the attacker. For example, a strong password is one that tends to be difficult for an attacker to crack. Ideally, we would like to have it be impossible, but the best we can say is we can make it very difficult. A weak password is one that is considered to be easily broken by an attacker. Not only must data within a database be secured, but attention must also be given to how data is accessed from and sent to the database. Products such as Oracle Database provide ways that enable the protection of client connections and the encryption of data that travels across the network between the client and the server. Using encryption for network data provides a degree of privacy that unauthorized parties would be unable to view the plain text data that passes across the network. Rather than sending plain text, we would use encryption and send what would be called ciphertext, kind of disguising the content. The importance of security for the network is the result of various types of attacks. Here are two types of attacks that we want to bring to your attention. Data modification attack. An unauthorized party intercepting data in transit could alter it and retransmit it. For example, intercept a $100 bank deposit, change the amount to $10,000, and retransmit the higher amount. The bank receives the deposit request for $10,000. The other form of attack that we wish to mention is what is referred to as a replay attack. Repetitively retransmitting an entire set of valid data. We intercept a $100 bank withdrawal and retransmit it 10 times, thereby receiving $1,000. One of the challenges to learning and understanding the details of any discipline is to first acquire an understanding of the terminology of that discipline. Computer security is an interdisciplinary arena, so there's a great deal of terminology that we need to understand. Here are some of the terms that we've used in this presentation and will continue to use in our discussion of cybersecurity. The term adversary could also be referred to as a threat agent. This could be an individual, a group, or an organization, perhaps even a government, that conducts or has the intent to conduct detrimental activities. An attack is any kind of malicious activity that attempts to collect, disrupt, deny, degrade, or destroy information system resources or the information itself. Recall that we talked about the CIA triad, where we had confidentiality, integrity, and availability. An attack could apply to any one of those three areas. A countermeasure is a device or technique that has as its objective the impairment of operational effectiveness of undesirable or adversarial activity, or the prevention of espionage, sabotage, theft, or unauthorized access to or use of sensitive information or information system. As we provide these definitions, we see that cybersecurity is not very narrowly defined, but it's a very broad area that we have to consider in terms of securing computer systems and the data that we've entrusted to those systems. A couple of additional terms are presented here: security policy, system resource or asset. We've also used the term risk, threat, and vulnerability. As you try to digest what I've presented here and these terms, consider the challenges related to validation of mechanisms and policy with respect to threats. The challenge is determining the correct set of assumptions regarding the adversary, that is, the threat model. We often have 20/20 hindsight. It's easy to know the right thing to do after something has happened, but it's hard to predict the future. We presented our motivation for investigating data security. We've noted that security features are recognized to constitute additional costs and add overhead to a system. The result is potential performance degradation. Additionally, employing these features leads to higher system complexity, loss in flexibility, need for human resources for design, management, and maintenance, and a need for additional hardware and software. But on the other hand, it's also recognized that if you fail to take proper security measures, you expose the system to risks which might bring about heavier costs upon system failure. The cost of taking no action and incurring some kind of a system failure or data breach could be more severe from a financial perspective than the cost of implementing some security. The point is, there's really no free lunch. We hope you found this video to be useful and informative. If so, consider giving us a thumbs up. In future videos, we'll discuss a variety of security-related topics that include encryption principles and how encryption techniques are used to provide confidentiality for transmitted or stored data. Our investigation will consider both symmetric encryption and asymmetric encryption. We'll also investigate cryptographic hash functions and their role in message and user authentication. Consider subscribing to the channel to be informed when we post these videos. And once again, thanks for watching.